All right, so I decided to do the talk on text processing. In particular, this was kind of inspired the Quora Kaggle problem that's up right now that ends this month. Takuya's group, the Cleveland Data Science R Python Julia supergroup, whatever that's called, they met and worked on this problem, and I started vectorizing the doc and talking to people about it, and I quickly had to define vectorizing a doc and other things like that. It was just clear that other people weren't working with text a lot, and so that hit me that we've never done that as kind of an intro topic here. So I thought we'd go through and just talk about how do you deal with text when you want to do mathematical model. So a couple quick notes about me. I'm the Senior Director of Data Science at Dialogue Tech, organizer of this group. Recently put up a video series on PacketPub on getting started with some of the packages like Carrot and things in machine learning. In the slides that I'll put up, I've linked to GitHub, Twitter, LinkedIn, all those things. So I won't read this word for word, but just natural language processing obviously is computational linguistics. All these fields, text mining, all fall into the areas of just helping computers work with unstructured text data. Mainly today, what I'm saying at the bottom here is that we'll kind of focus on this with an aim towards machine learning, but really focus sort of on the processing step more than the machine learning after it. Once you've processed it and you've got it to numbers, at that point, it should be fairly straightforward if you know what you're doing with machine learning to go from there. You can cluster, you can do all different kinds of things. So I'm going to do this kind of and I talk about this towards the end of the presentation as well. I'm going to do this using more traditional packages. There are other approaches you will see using some newer packages, specifically tidytext, which kind of fits in with the tidyverse way, or as we've called it here at the group before, the Hadleyverse way. But this is using more traditional R library. So this is the text mining package. You load it up, and for the purposes here, I've created very, very simple toy text data, which fires a lot of people up in presentations. They want to see you work on real data, but when you're looking at the structures that we're looking at, it's very, very helpful to have extremely simple data at first to see what we're looking at. I think that'll become obvious as we go along. So one thing to notice before I go on is just, okay, obviously you've got some similarity between the first three lines. The first and third are exactly the same, but the second, they all have happy birthday in it, and the last doesn't really have anything in common, in terms of the actual words in it with the lines. So I won't keep flipping back to the slide, but just kind of keep that stuff in mind, and it'll help. So to start with text, you create a corpus. This is a fancy word that just means body of text. There are corpuses built into these packages. For the Reuters corpus is a famous one for working with text, which is a bunch of news articles from the people at Reuters. You can load up, there's a Jane Austen package, things like that. There's all different kinds of ways of getting sample bodies of text. But this is sort of the default structure for data in the text mining package. And then this TM map allows you to run the document through a variety of content transformers. So you see the second one here, pretty obviously I'm stripping white space with it. The last one, you'll notice it's wrapped in the function contents transformer. That's because toLower is just a default R function and not built to do this on a corpus. And so by wrapping it, it just does some things that makes it friendlier to work on the text mining structure. So if you look at the structure of it, obviously there's a lot here. There can be metadata and things like that, depending on how the file's loaded up. The main thing you're going to recognize here, right, is that there's a list of documents. The first one's content is the line, right? And if you notice, I said I wouldn't go back a bunch, but everything, capital letters. I forgot I should have put in some punctuation. We've run it through some processing to strip those things out. Everybody good so far? So now we'll create a document term matrix. This is a mathematical representation of the document. And so I'm passing default arguments here. So this is going to be a count vectorizer. So essentially, and we'll look at it in a moment, but each row is each document. Document is a bit of a stretch in this case because it's 4 or 5 words. It's a sentence, but each row is a document and each column is a unique word. And then the value in that matrix is the count of that word in that document. When you just look at it by default, if I put it out to the REPL here, you see that it's actually just saying it's a document term matrix. It's giving me the sparsity of that matrix, but it's not actually showing me that matrix. If I do inspect on it, let me fix that real quick. It changed resolution on me, so it's going to be easier if I fix that real quick. Bear with me here. I thought we had a 1080p screen, and it's not. Okay, so that's what we were seeing when we just put out the document term matrix to the terminal. But if we inspect it, we see, and this is what I was talking about, the structure of each document's a row, and you see the word as the column names and the count there.
You probably said what's sparsity meaning?
So underlying, it's using a sparse matrix, and so it's optimized for sparse data where more of it's going to be zeros than ones, and so that's telling you the percentage that's populated of the data. You can call as matrix on it, and you need to do that in some cases for machine learning out, but at that point you're creating possibly a much larger data structure. In this case, it's simple. There's not much, it's a lot of words in common, but you can imagine, if these were lines of text in something the size of the Bible, you're going to have zeros. You could have a vocabulary of 20, 30, 40,000 words, and most of those are going to be a zero value. So another way to make a document matrix is going to be TF-IDF, term frequency inverse document frequency. I'm not going to walk through the math here, but essentially it's a ratio of the word in the document to how often the word appears in the text. So it essentially penalizes it for being a more common word in the body of text. So the higher values in a TF-IDF matrix are going to represent words that are in the text that are relatively unique. So obviously when you're thinking about trying to classify the differences in documents, that's a useful thing. That's a pretty hot area in NLP these days. So we do that by passing into the document term matrix some control parameters. And so you see here the whole TM library and some of the libraries that work with it take these. It's this convention of you pass in control, which is a list, and that's named arguments, essentially wrapped up in a list. When I inspect that, you'll see now that the values down here are floats, and these are the TF-IDF values. Everybody good so far?
Weightings can be corpus-wide or per document?
So it's the ratio of term frequency in the document over frequency in the corpus. But I want to say in most default implementations, the frequency in the corpus, like it's run through a log or something. There's a couple different variations, but so one of the things you can do, like now that you've got it in this mathematical format, a pretty common thing is to ask for frequent terms. So we've set a threshold here at the top. Any term that shows up at least twice, we see a list of that. On the bottom, if that document term matrix is a TF-IDF matrix, then that's threshold is still a TF-IDF threshold. It's no, you can't say If I'd have put 2 in there, it would have returned 0, even though there are words that are in there twice. Because it's just searching for that value in the matrix is all it's doing. That value or greater. So from there, a common thing to do is topic modeling. On a real body of text, this matrix might have, you could easily, like I said, be 20, 30, 40, 50,000 features or columns. And so that's not very wieldy for a lot of things. A lot of things that might require inversion of that matrix at that point aren't possible. And so pretty commonly you would want to decompose your matrix as it stands anyways with something like PCA. The preferred way of doing that with document vectors and matrices is either LDA or NMF, which are I'm listing up here. And part of the reasoning is that you can actually go backwards and trace those two values. What I mean by that, so PCA, without going into too much of the math right now, is a very complex rotation of the matrix. And at that point, each new column is not, it's destructive. It's not clear what those values represent in the prior version of the matrix. There's an argument, if you don't, that's assuming you reduce columns. Let's not split hairs here though. The point is, NMF and LDA, you can actually say, okay, this topic is tied to these couple of words. And so you actually would tend to look at those and see associations, right? Note that you don't control those topics. This is not like modeling saying, I'm going to explicitly name sports as a topic or happy birthday as a topic here. These are naturally appearing associated words that are related in the documents. So let's do this and maybe that'll help make a little more sense. So I'm loading up a library I'm using for it that works nicely with TM structures, text mining structures, and that's topic models. You see the call here to LDA. That K parameter is the number of topics I want to have. Since again, I'm using very simple data, I've just said 2 topics. And kind of different, if those of you used to machine learning type functions in R, a lot of times predict is how you apply. And in this case, it's posterior you apply with. LDA kind of has a Bayes bent to it, so this sort of makes sense in that world. The structure you get out has a matrix here you see called terms, and that actually shows you, there's not a lot you're going to learn or apply out of that, but each row here is a topic, and then the column is a word. And so you're actually seeing, okay, to look at topic 1, this is a waiting for the word and, this is a waiting for the word birthday. And that's how you would apply and get the scores out. This topic matrix at the bottom is actually, and it's kind of cut off here. Let me see if I have it on the next slide. It's not great. Let me change something real quick. Okay, so if I put out just that portion of it, you can see here, this is the columns of the topics and the rows of the documents. So it's a compressed representation of the document. It's now numeric. One thing to notice, remember the first and third lines were exactly the same. You'll notice the topic values are exactly the same. So if I take that same topics, I'm giving it clean column names here of topic 1 and topic 2, and I put it in a data frame with the lines of text. Now you have kind of a full data set of, okay, here's the lines of text, here's the topic values, this is processed and ready for machine learning at that point. So one thing you could do is plot it. Let me kill and restart this one because, so there's a random factor to the LDA, and the numbers, the jitter values, you have to guess. I'm plotting, and these two blue dots are the same, right? And they would overlap each other, but I'm using geom jitter to get them to move. But the scaling is different every time because there's a random factor. So now they look way far apart, but most of the time they look the same. This is why you should set seeds for presentations when you're doing random numbers. But the point is, you can't read the labels here because the font size's bad, but the blue dots are jittered out separately, but those are happy birthday to you. The green is happy birthday dear, happy Cleveland R user, and then many more is down here. And so it's kind of even worth noting, like, those topics aren't necessarily a great linear representation of, like, you can look at the green dot has happy in it, the blue dots have happy in it, and the red dot has many more. You know, like you might not think that those distances look right, but they're also shorter sentences. There's multiple ways to look at this. So one thing, for instance, at this point you can cluster those documents. I did 2 clusters, one with 2 centers, one with 3 centers. Again, the resolution is kind of causing problems here, but the gist of it is the 2 clusters. Obviously, it puts the same on the 2 identical lines. Kind of interesting to see. Again, it clusters and many more in with that, and the longer sentence with Cleveland R user separately. On the 3rd cluster, let me again just pull out the 2nd cluster because it's putting line names together with it. So at that point, when you have 3 clusters, it figures out to make the second line its own line. Similar documents. So an approach to this is to do cosine similarity of the documents. Again, not going to walk through the math here of it, but it's essentially a multiplication, like a dot product, not dot product, excuse me, element-wise product of the various topics. So you're looking for, obviously, the larger the similarity, that means that they each had values in the same topic that were significant, right? If one has a large value and the other has, 0.0001, you multiply them together, you're not going to get much, right? Whereas if you have fairly significant topics, they're going to be sizable. So the largest value that you get out, that's your most similar document. This LSA package works nicely with these matrices. One oddity to the cosine similarity is that it wants the matrix transposed. Where everything else, in machine learning, you think of it as your observations are rows. In this case, it wants your topics as rows and your documents as columns. But what comes out is a square matrix. So at this point, you see, obviously you've got a 1 all the way down the diagonals because that's comparing each document to itself. But if I want to see, for example, the results or rankings for the first document, if I just take the first row, that's what I'm doing down here. And then I can get an index by saying, give me the order of that. Order, remember, isn't going to give you the values, it's the indexes of them. And then I'm reversing it, so I'm getting a descending value. So now index is telling me a ranked order of, okay, the 3rd document is most like the first document, keep in mind they're a tie because they're the exact same document, and then the 4th, and then the 2nd. So now if I use that to index the text and to index the results, I now have a ranked list of documents most similar. And actually, like those of you, so we work with Elasticsearch a lot, like this is actually pretty close to how Elasticsearch does its search. It's LDA on, but they do it on term frequency as opposed to a count vector. But that type of score is what you're going to see when you see a document search score. Something else about that I was going to point out. Oh, one interesting note. A ways back, I heard the Netflix CTO, it's probably not the Netflix CTO anymore, but talking about this of they were doing something similar to this with users against other users on the same movie. And when they have millions of users, you end up with these square matrices of millions by millions of rows. That was actually their specific driver that got them out of MySQL and into, I believe, Hadoop, but because they weren't able to process at that point these type of matrices. So like what next from here? The tidyverse approach does this a lot different. There's a book that's free online, Text Mining in R, that shows that approach. I've started through some of that. I didn't feel comfortable enough including it in here, and I'm still sort of mixed on how I feel about it versus this approach. But if I get further in that and decide it's worthwhile, I might present that here. The tidy text package is what's included there, but it uses all the standard tidyverse stuff. For those interested, word embeddings can be an interesting thing to look at. If you're not familiar, this is things like Google's Word2Vec and stuff like that. This is where you actually get into the differences between words have meaning. So you actually get the ability to what's the standard example that Word2Vec gives of all is of like king minus man equals queen. You can actually do some math that comes out with things like that. And it's a different way to represent your documents, a little more complex, lend itself to different tasks. So it's just different tools, different jobs. WordNet 2 is another interesting area. Again, all these kind of topics are larger than where we're at today. So I do have a quick other example that I thought I'd bring up that's like legit code on a larger size piece of data. But before I do that, pause for a second for any questions or got a couple in the back. Okay.
This is a somewhat indirect question, but some academic books on NLP focus on things like decoding the grammar, ontology hierarchies. And I was just wondering if you ever use those types of approaches for your tax work.
So our main use case at work, we deal with a lot of conversations, transcriptions of phone calls. We do pretty simple things to just clean up the text and get rid of. So something I didn't show in here, and I think I had, and I pulled it out. Stop words is a real common thing. I probably should have showed that. And that's where you simply are pulling out like and, or, but, just things that have that have meaning in context. But keep in mind, once we've converted to that matrix, we've lost context, word order, association. So even words that you'd say, well, not is a negative word. Yeah, but what's it negating? In the representation we're working with, it doesn't have much meaning. So we do some of that. You can get into more, obviously stemming is a common one where you're just getting to the root word and looking at similarities. In terms of even beyond that where you're talking hierarchy and things, I don't work with that. The closest, we have played around with some examples with embeddings, other members on the teams, and that gets closer to what you're talking about.
Thanks. Do you think it's unusual to use that approach outside of academia for anything?
I wouldn't say it's unusual. I think when you look at, so with Word2Vec with Google, for example, they're at times truly trying to, they do a lot of natural language processes, frameworks will do named entity recognition, for example, right? Just pulling out proper nouns, names, places, those type of things. Google takes that a lot further when you look at the information that they're pulling from web pages these days that they actually will present an answer on the search page to your question. At that point, they're really looking at extracting meaning, and so I think you have to get into those approaches. For us, our major product around this right now is all about classifying of calls. So if you're you're, for example, you're in the audio industry. Was that a parts call, a sales call, a service call? Well, that's pretty straightforward machine learning classification. We don't need that level of semantic understanding of what you said on the call. But I'm sure there's places, Google, I would say, is outside academia and doing it. I don't know if others have other examples. Or
Yeah, thank you. It seems like there's a split in the books between, counting words, for lack of a better way to say it, and that meaning approach. What do you think of the book Taming Text?
So that's on my never-ending stack of books that I have not read yet. But I've had that recommended before. There's a couple good ones with this. There's another question again?
Yeah, so when you did LDA back a couple slides ago, is that distance Euclidean? Resulting distance matrix?
No, I do not believe so. So there is, what's the LDA that's pure decomp? There's two things in here, and you can, if you just start typing LDA in R, you can get the wrong one very easily, depending on what packages you have loaded up. This is,
you're thinking of like linear discriminant.
yeah, yes, and that would be Euclidean. This is not.
No, it does give you a metric. I mean, it's a metric in a sense.
Yeah.
Distances are distances are metric, right? So it's a metric. It's a real metric.
It's a real metric, but yeah, I don't think that's where I was saying, like on the plotting, I would not interpret the distances as having meaning.
I was just also interested that you use, in the fact that you use k-means to cluster them as well, being that one of the criteria to actually use it is the fact that you need Euclidean distance.
Yeah.
Whereas like in text, you would use something like a Levenshtein or a Jacquard.
Jacquard or
Yeah, so typically I would see clustering more commonly on NMF, or even on PCA where it's destructive and you're not going backwards. No, I would agree with that.
You got to remember after that latent Dirichlet allocation that's in these are real values now, so Jacquard doesn't really apply. It's not like we're just looking at 0 to 1 to 4. These are continuous values.
Sure.
And it's a metric, so I mean, actually k-means would apply to it. It's not a standard application of it, but it should still apply.
Yeah, I mean, mainly I was looking at the simple of like it was picking up on, obviously exact same lines, which is not a hard pickup. But so this is an example from the stuff I like I said, I was doing a video learning series, and so I'm working with a more real set of sizable data there out of the text-to-vec package. You'll see me loading it up. I don't use any functions from text-to-vec. We're just getting a data set out of it. Loading up Caret, topic models, and then this movie review data set. This is a bunch of IMDb movie reviews with sentiment. And I'm skipping the like exploratory analysis stuff here, but this is a more common. So there was some like markup and stuff in there. So I'm stripping it down to just alphanumeric, and you'll see in here I have more transformers. So I've wrapped this removing special characters, just like 2 lower. It lets you write a simple R function and wrap it. Remove punctuation, stop words, those type of things. So I'm going to cheat here in a second. Load up a document term matrix, and then you can call inspect on that. And so you'd see, it's not really great. Let me bump it up. So apparently everything in these reviews has numbers in front of it. Let's try. Yeah, so there again is kind of normal, unique words. Something to notice here, I mean, the number of columns is 51,000. I mean, that's a ton of terms, right? So now all of a sudden you see why I'm getting into, like, you have to get into topic modeling or some kind of other decomposition of your matrix, right? You're not going to want to do real math on that. And speaking of, here's where I cheat. So amongst other things, I'm only using a subset of the data. I used a stratified split out of Caret to get 20% of it to do the LDA. A lot of that's common advice online you see of like, unless you really have the time, just let your machine sit and run for a couple days. You can't put the entire body of text at it. I'm actually not even going to run it here. What I'm going to do, I saved it off. For anybody who doesn't know this, save RDS just saves an individual R object to file, and so I can cheat and load it up from disk where I already ran it. And so I'm doing a Caret split, 70-30, XY test train. If you don't know machine learning, that's fine. And this is a really terrible model to throw at it that will give me warnings. But the whole point is just to show you can do some simple classification, right? I'll do prediction on those topic models, spit out the confusion matrix, and you see where did it wrap?
You did like a logistic, good or bad.
Yeah. Why is it not showing the accuracy number? Oh, it broke it down to here. So it's just because of the wackiness of the resolution, but let me try it again. There we go. So it's 74% accurate at guessing the sentiment of the review. It's a 0 or 1, which again isn't great. The point isn't here. We're not hyper tuning a model, but if I cluster on those, again, I'm going to cheat and just load the. So then I can put out like a table. So there's a crosstab of down the left, I've got clusters, and then I've got sentiment here. And so you can kind of look and just see like, okay, do I have a cluster like this where it's like 2 to 1, positive to negative? What's going on with that? I had one, it was interesting. I looked and it was all the wrestling movies in the cluster, like WWE and yeah, like documentaries or like, yeah. And they were enthusiastic reviews. I forget what I do in this last one here. Oh, again, so I'm going to load up, because this is cosine similarity. Box plot isn't that meaningful. The real thing I wanted to do with this one was, so there's like a documentary about Michael Jackson. That's one thing about this set, it doesn't give you the title of the movie, so you just have to like start reading the review and kind of figure out what movie it is. But this is obviously about Michael Jackson. And so if I take this index is the top results, and the next one here, okay, I should have indexed that out. It was giving the exact same one. War of the Worlds. I don't know where it makes an association there. Kind of a Jurassic Park one. This isn't great. Again, set seeds. Find what you're doing. But yeah. So in general, the point is you can get from these raw texts to mathematical representations, and amongst other things, the main thing I would say is think about what your use case is, right? Like, stop words matter in some use cases and some they don't. If you're actually trying to get similar utterances and it's relatively short, I would probably leave those words in to do that. If you're really looking for meaning in long bodies of text and similarity, then you're looking probably for more unique words and things like that. But yeah, as I mentioned, at the Core Kaggle meetup, it seemed like this area of stuff wasn't well covered, so I wanted to do kind of an intro. If anybody wants to come back and do more advanced, you're welcome to come talk.